So, in the area above AC and BC, the two components are present only as a homogeneous liquid solution. So, if we consider this area here, we get only one phase. Okay, this is homogeneous liquid solution. Okay, so we get homogeneous mixture. Okay, so there is no heterogeneous mixture here. As phase 1 here, it is bivariant, meaning that to define any point here, it is necessary to specify both temperature and composition. So, here number of phase is only 1 here. So, our phase modified phase rule says C minus P plus 1. So, number of components again 2, but phase is 1. So, plus 1. So, 2 minus 1 plus 1 gives you 2. So, we need to specify both temperature as well as the composition mixture. Okay. So, suppose for this point, okay, so we get a composition like here. So, this is the composition as well as this is the temperature, but still we are in the one phase region. Or if we consider here, okay, again we need to define both temperature and composition mixture, because still we are in one phase region. If the composition of the original liquid at the right side of the eutectic point, as represented by point X, is cooled at a constant pressure, the temperature will fall without any change of composition B until the point Z and until the freezing point curve on BC is reached. So, if we start from point X here, and if we cool down, or if we cool down this one, keeping the pressure constant, we reach at point B here. So, on the freezing point curve of BC, we reached here. On reaching Z, the solid B separates out. Here solid B separates out, but we still get two phases, right? One is along this line. One is solid B as well as a liquid solution of component A and B both. As cooling continues, B keeps on separating and the solution becomes richer and richer in A. So if we further cool down here, okay, we get solid B separates out, and then the solution becomes richer. So we get more and more A here. The temperature and the composition both change along ZC. Okay, along ZC, if we see, okay, so temperature and composition both change along ZC. Again, when the eutectic temperature is at point D here, A begins to separate out. So this is the eutectic point. So if we consider this line here, we reached at point D. So at point D, A is now beginning to separate out. The system is now becomes invariant. Again, it is becoming invariant. On withdrawing heat further, the temperature remains constant and solid A and B continue to separate in the same ratio. So the solution compositions also remain constant. Ultimately, the solution phase solidifies completely and they are coexistence of two solids A and B. So here we get two phases, solid A and B here. Now we consider one example. This is lead silver system. These metals are completely miscible in the liquid state and do not give rise to any compound formation. Pure lead melts at 327 degrees Celsius. So pure, this is component B here. So pure lead melts here 327 degrees Celsius, and the addition of silver lowers its melting point along BO. So if we keep on adding silver here, so this is 100%, at this point 100% lead, and this is the point where we get 100% silver. So we keep on increasing silver along this direction. So if we just keep on adding silver here, okay, so we get this curve BO. Okay, so this BO is the freezing point curve of lead containing varying amounts of silver. Similarly, pure silver here, it melts at 961 degree Celsius, and AO, if we consider this curve AO, is the freezing point curve of silver. The system at constant pressure is monovalent along AO, okay, and AO and BO, okay, AO and BO, and the pressure is constant again here in this phase diagram. O is the eutectic point, like before. O is the eutectic point. where solid lead, solid silver and their liquid solution coexist. It has 3 phases and is thus invariant. Like before we discussed, its temperature is 303 degrees Celsius and this is the composition mixture. Okay. So 2.6% silver. So when we have 2.6% silver, okay, and the rest is your lead, okay, and temperature is 303 here, then we reach at eutectic point. The lead containing a small amount of silver is first heated to a temperature well above its melting point. So lead containing a small amount of silver. So small amount of silver is this side, lead contain mostly lead. So we started with point P. So the system consists of only one liquid phase at point P. Like before, you get only one phase here. Okay, we started with one phase here with liquid silver and liquid lead. So we started from if we start from point P and then if we cool down like before, when the cooling takes place along AB, at B lead crystallizes. Okay, so along actually Q here, okay, lead crystallizes, not B. Along PQ and at point Q, lead crystallizes. The solution remains with relatively increasing amount of silver, but we have, since lead crystallizes out, so we have now more silver here. Then lead continues to separate out and the melt becomes richer with silver until the point O, where the percentage of silver rises to 2.6% here. Okay, 2.6%. This process of raising the relative proportion of silver in alloy is known as Pattinson process. So this process is known as Pattinson process. These metals are completely miscible in the liquid state. Okay, so as I discussed, these two metals, they are completely miscible in liquid state, and then we are decreasing this temperature. So now we discuss phase diagram of 3-component system. Now we move to 3-component system. For a 3-component system, the phase rule becomes F is phi minus P, right? So again we have the initial equation like F is C minus P plus 2. Now C is 3 here, so we get F is phi minus P. Here 4 variables would be necessary to define a system, which is difficult, right? So we need to define 4 variables in order to define the system. So P and T are fixed. So here both pressure and temperature we are keeping fixed, and a triangular diagram is used to describe the system in terms of the remaining variables, 2 of the 3 concentrations. So basically what we do here, we draw one equilateral triangle here, and we are having now 3 components, A, B and C. So component A, okay, so increases along this direction. Component B increases in, okay, component A increases in rather this direction, if we say. Component B increases in this direction, and component C increases in this direction. Okay. So basically component A, this is 100% component. So component A increases in this direction, component A increases in this direction. Component B increases in this direction, this is component B increases. And component C increases in this direction, C increases. Okay, so here P and T are fixed, pressure and temperature are fixed. So the corners of triangle levels at A, B and C correspond to pure component. The side of the triangle opposite to the corner A implies the absence of A. So what it said is like that. So along this line BC, along line BC, no A present, right? As I mentioned, concentration of A increases along this direction. So along line BC, there is no A, okay, and so it is like your 2-component system. So along line BC, we have only 2-component system, okay. Similarly, along line AB, there is no C. Okay, as mentioned, C increases in this direction. So along this line there is no C. Okay, so again along line AB we get only two component system, component A and B. Similarly, along line AC there is no B present. Okay, no B component present. So along line AC we have two components A and C. Thus, the horizontal lines across the triangle show the increasing percentage of the compound from 0 to 100% at the apex. So A increases in this direction, and when A reaches here means we get 100% A. Similarly, B increases in this direction. When we reach at point B here, we get 100% B, and so on. It is possible to read of the composition at any point from the three composition scales of the diagram. Okay, so you can take any composition mixture like your A equals to, suppose A is your 40%, B is your 40%, and C is 20%. So if you follow this one, like A increases in this direction, B increases in this direction, A increases in this direction, B increases in this direction, and C increases in this direction. So from there actually you get a point, okay, on this diagram, which represents that composition mixture 40%, 40%, and 20%. Okay. So the total composition is always 100%. So if you add them, 40 plus 40 plus 20 will 100%, because of the geometrical results, and that the sum of the three perpendicular distance from any point to the three sides of triangle is always equal to the height of the triangle. So next we discuss a liquid equilibria. So the simplest three component system are those in which a liquid breaks down into two phases. The system is acetic acid, chloroform, water. Here the system is said to be in a state of liquid equilibria because it forms two separate partially immiscible liquid phases at certain concentrations. Right. So if we consider here, this is the liquid acetic acid, water, and chloroform. So acetic acid increase, concentration of acetic acid increases in this direction, as I said. Concentration of chloroform increases in this direction, and concentration of water increases in this direction, right. So along this line, water, chloroform, this line, we have only water and chloroform. There is no acetic acid along this line, right. Similarly, along this line, water, acetic acid, there is no chloroform, and along this acetic acid, chloroform, this line, there is no water along this line. Now this is a line, or this is a curve which actually meets at this water and chloroform. So it says that water and chloroform, they are completely immiscible with each other. Okay, completely miscible. Otherwise, we would have got a point starting from here and ending it here. Okay. So what I said here is, if we suppose we get a curve like this instead of the one drawn here like this, so we would have got, okay, this region and this region, okay, they are completely miscible. Okay, these two components. Okay, but along within this curve, those components are immiscible. But since this line meets at point here and here, it says that water and chloroform, they are completely immiscible with each other. Okay, so the system, okay, fine. Okay, so a two-phase region occurs in a relatively low amount of acetic acid. Okay, so if we add very small amount, now acetic acid increases in this direction. So if we mix water and chloroform, suppose we started with somewhere here 50% of water and 50% chloroform, and then if we add acetic acid, okay, here we end up with again two phase, as I mentioned. So region inside this curve we get two phases, okay, and outside this curve we get only one phase. Okay, so outside this curve one phase means in this region water, chloroform, and acetic acid, so if we mix them we get only one phase. But here in this region if we add small amount of acetic acid, as I said, acetic acid increases along this direction, right? Along this direction acetic acid increases. So if we add a small amount of acetic acid, suppose we reached at this point here, okay, or if we consider a point like here, so here we suppose we consider a point here. So what is the concentration of acetic acid here? This is your 10%, and this is 10%. This is 20% acetic acid here, right? We are using 20% acetic acid. Okay, so if we add 20% acetic acid, start from 50% water and 50% chloroform, there is no acetic acid at this point here. At this point, there is no acetic acid, as I mentioned. Now, if we keep on adding acetic acid, we reach that point there 20% acetic acid. Still, we get two-phase system, right? Still, we get two-phase system because it is falling under this curve. If we keep on increasing acetic acid, and then we can reach at point here somewhere, okay, and just above this point we get only one phase. The tie lines of two phases region, okay, so the tie lines in the two phases regions join the composition of two phases that are in equilibrium. So these are called tie lines, okay, these are called tie lines. This is the tie line. So this is the tie line, this is one tie line, this is another tie line, and these are called tie lines, okay. So these tie lines, okay, so these tie lines says that the two phases that are in equilibrium with each other. So you get, if we consider this tie line, it meets here and here. So you get two phases, one is there here and another is there. So one is with your rich in water with small amount of chloroform, another is your rich in chloroform with small amount of water, okay, and so on. So if we take this composition mixture, so we get two phases, one is having composition this, another is composition this. Now why this tie line is slanted? Okay, next. So these are slanted because it represents, okay, so in this phase the solubility of acetic acid is different from the amount of solid acetic acid present here in this composition. That's why the tie lines are slanted. Okay, so if we had we have like the concentration of acetic acid here and here both are the same, then we would have got a line or tie line parallel to this axis. Okay, so these tie lines are slanted because the miscibility or the solubility of acetic acid in these two phases are different. That's why these tie lines are slanted here. So the tie lines which are experimentally observed are no longer horizontal. So here for this case these are not horizontal. Thus is total composition at any point in the two phase region gives two compositions, right? So yeah, you get two composition as I mentioned. Thus a point D on the boundary is similar to the critical solution temperature and is called the isothermal critical point or the plate point. So if we, as I said, you reach a point here somewhere along just any point along this line, okay, at point D, okay, so this is on the boundary, okay, boundary between one phase and two phase is similar to the critical solution temperature or is called the isothermal critical point or the plate point. So this point along any point along this line is called isothermal critical point or the plate point. Means just if we reach this point, you get still we have two phases, but just if we increase little more, if we add little more amount of acetic acid, we get one phase right here. Okay, so this point is called the isothermal critical point or the plate point. So now if we application of the phase rule or to a system corresponding to a point in the two phase region gives F equals to 3. So what is the phase rule says? Okay, so phase rule says F is 5 minus P, right? So 5 minus P, F is 5 minus P. Now this is two phase region, we are considering two phase region here. So for two phase region, this is 5 minus 2, so gives you F is 3. But we are keeping pressure and temperature constant. So here P and T constant, right? So we get, we have to subtract these two. So we get when P and T constant, then we get F is 3 minus for pressure 1 and for temperature 1, 3 minus 2 gives you 1. So, the 3 degrees of freedom can be accounted for P, T and one composition variable. Okay. So, one composition variable we get. We thus find that the composition of both the phases cannot be arbitrarily fixed. If one is fixed, then the tie line from that composition fixes the composition of the second phase. So, from the tie line if we fix one, from there if we fix one, then tie line, from the tie line we can fix the another one, because number of degrees of freedom is now 1. We are fixing pressure and temperature. Then we move to solid-solid equilibria. The solid-solid equilibrium exists in systems which can exist in more than one crystalline forms which have different physical properties and are known as allotropes. Each polymorphic form has different phase and transition in between them can take place. For example, sulfur exists in two crystalline forms, rhombic and monoclinic. The transition temperature is 95.6 degrees Celsius and 1 atmospheric pressure, at which they can transform into one another. It is also shown in the figure. Okay, so if you see the figure, okay, so here it is 95.6, and if you see this one, this is 95, this is 95.6 and 1 atmospheric pressure. So this is this point along. Okay, so below 95.6. The rhombic is stable, while above it monoclinic is stable. So, below 95.6 you get rhombic is stable, and below you get monoclinic is stable. Thus, under a pressure of 1 atmosphere, melting point of rhombic sulfur is 114 degrees Celsius, and for SM monoclinic it is 120 degrees Celsius. So, this is 120 and this is 114. Okay. So, the liquid form or L undergoes changes in color and viscosity when heated and boils at 444.6 degrees Celsius. This is the 444.6 degrees Celsius. Thus, sulfur can exist as 4 possible ways: rhombic, monoclinic, liquid and vapor. But all 4 cannot coexist, because according to the phase rule. Okay. So, because the number of phases coexisting in one component system cannot exceed 3, because F is C minus P plus 2. Okay. The curve AB is the sublimation curve of SR. So, this is the sublimation curve of rhombic sulfur. Okay. Because you get solid sulfur and vapor sulfur, they are in equilibrium with each other. Okay. Here rhombic sulfur and vapor exist in equilibrium and is monovariant. So, this is monovariant. The curve BC is the sublimation curve of monoclinic. So, if we consider the curve BC, here you see, so this is the sublimation curve of SM. Here SM or monoclinic sulfur and vapor coexist. Okay. Point B and C are the triple points. So, here we get the triple point, 2 triple points here. Okay. So, in this triple point you get rhombic sulfur, vapor and monoclinic sulfur, right, at point B. Okay. So, the curves, okay. So, the curve CD is the vapor pressure curve of liquid sulfur. So, if we consider this curve CD is the vapor pressure curve of liquid sulfur, because here have the liquid phase and this is the vapor phase. So, CD represents the vapor pressure curve of liquid sulfur. So, this is also monovariant. The curve BE is the transition curve which gives the effect of pressure on the transition temperature of SR and SM, right. So, this curve BE, okay, is the transition curve which gives the effect of pressure on the transition temperature. So, we are plotting pressure and temperature here. So, this is the gives the transition temperature between SR and SM. The curve CE is the fusion curve for SM. The curve CE is the fusion curve of SM, because you get SM and liquid, monoclinic sulfur and liquid, they coexist along this line CE. That is why the curve CE is called the fusion curve of SM. Again it is univariant. The curve EG, we say curve EG, okay, here you get solid rhombic sulfur here and the liquid phase, they coexist. So, the curve EG is the fusion curve of SR, it is also monovariant.